I will start now. My name is Ahmed Youssef. I'm a software design engineer at Valeo since 4 years. I am an expert in the validation of algorithms inside the organization, and specifically, I am working on integration of simulation platforms or virtual platforms inside the testing tool chains, including hardware in the loop, Hill, software in the loop, and MIL, so model in the loop. I am working on products such as ultrasonic, LiDAR, and radar. I want to present today how and what is the important aspects of integrating virtual platforms inside the pipeline from the point of view of tier one supplier, because what we do is more of a component test, component validation, algorithm validation, and so on. So I will start with an introduction. So long time ago, people were using horses to go from A to B, from one point to another. They were using the horses to move objects, cargoes from one city to another, until a guy came from Karlsruhe, from Germany. He is Benz, and he invented the first car, which in his idea was to simulate or emulate the horsepower into an engine. And this was the first revolutionary aspect that what happened. But after that, the knowledge, the science was improving very, very fast. So people said, okay, we are moving with cars, and we have a co-driver, your wife, your husband, which always tells you, yeah, go left, go right, holding the map, holding your coffee, telling you, please, let's go to the bathroom, and so on. And the science said, okay, let's virtualize this co-driver. And now this is what we reached till now, which is having GPS, having some monitoring systems for the eyes. If you are tired, you are getting notified, please take a rest. So this was the first step to virtualize something inside our modern cars, which is the co-driver. In addition, we have some systems such as a lane keeping system, blind spot detection, and auto parking, which helps the driver actually to make some functions, and all this in order to increase the safety on the roads. And as we are going further with our science development, the science wants to also to virtualize the driver into what we call a full autonomous cars or vehicles, which is, as we know, that it's the level 5 autonomous driving concept. So this is a video which shows one of the cars. I need to play it, maybe not in. Let me check. So this is the new Audi A8. It was released in 2018, which has some functions such as laser scanner functions, or ultrasonic radars, MMIs, and front cams, which is able to do up to level 4 functions and systems such as lane keeping and lane changing. And this was the first car which has the laser scanner from Valeo, and it was tested by the Minister of Transportation in Germany in one of the highways in Germany. So as we can see, we have some detections from the fusion of the different sensors and systems, and is able to do some traffic jam alert, ACC, adaptive cruise control, lane keeping, lane changing, blind spot detection, and auto park. This was released, I think, in A8, and now we also have it in A7. So this was one of the cars which has the laser scanner, which I'm working on. So let's go back to the presentation very fast. And so I want to first present what are the software testing challenges we have. So as we know that we have many driving assist systems. It's now more than 25 systems, such as I said, emergency braking, some pedestrian detections, the cross traffic alert, and some surround views, which are now available in many OEM cars. And sensor fusion is a big topic because of some priority on each sensor level, including cam, front cam, and radar, because of the difference in the ranges, field of views, and so on. And we are testing to ensure this functionality. We have many testing levels going all the way from component test, integration test, software validation and verification, and system test in order to reach this acceptance level, which we are trying to go forward what we call mission zero, which is a zero death in car accidents. And yeah, so this topic of ISO 26262, or the active safety, is very important in this aspect as we are going toward this mission zero. And of course, we are using dynamic testing in our department for software validation in order to test these functions, in order to cover all the corner cases, some customer tickets, some requirements on our scope. And of course, we have the trend of artificial intelligence algorithms, which is a very important issue we have, because till now, even the scientists, let's say, they cannot really predict what AI can do or what is the next step which this system is doing. As we know, when we test systems and functions, we spend a lot of money. Why? The car should be driven on a highway, let's say. The gas consumption, the depreciation of the car, the car cost itself, according to Ford, it costs around, to build a prototype, around $250,000 in order to build one prototype. In addition, it's time consuming, as we can expect that we need around 300,000 kilometers to only validate one function. So imagine 300,000 kilometers to be driven on a road for a certain amount of time. So this is it time consuming, in addition to having the engineers to validate, to test, to record the data, and going back to their desk in order to get some reports, bug fixes, tickets, and so on. So in total, the software testing is time consuming and it is cost effective when it comes to let's say testing using a car. In our company, if we want to test one function, we need to drive like maybe 10 cars in order to cover this mileage requirement from the OEM. And this is per function. So if we say we have 10 functions, we need like 30 million miles, and it's a lot. In addition to that, one of the challenges is the accidents. As we know, we have many accidents that are happening now and last year, especially when it comes to sensor fusion, pedestrian detection, object detection, and classification. In addition to some NCAP requirements, which we need to do or we must do, and this consumes a lot of money because we are destroying cars to make sure that it's safe. And this is one of the accidents which happened last year in London, where the car was unable to detect a truck because of some bugs in the algorithm, which says this was not a truck. I thought it is a bridge, and it went through a truck, and this is the accident which we see. And last challenge, of course, is the AI. As I mentioned, we have many algorithms that are AI dependent. We are using deep learning and DNN in some algorithms and functions in the organization, and they really need to be tested in many ways and try to cover as many requirements as we can, because as the dilemma says, who is responsible for the death? Is it the AI? Is it the engineer? Is it the company? Is it the OEM? Is it the tier one supplier? And that's why we should always ensure that the AI will act according to some certain limits which are defined by the norms and regulations inside, let's say, country or inside a defined standard. According to Waymo, this was in 2018. They reached like 8 million miles, and they are still counting. I think they reached 10 million already on the road, and we know that this is a lot of gas consumption and time consuming. On the left side, we can see the mileage and this engagements per the mileage that they already consumed. Google is now heading, which is Waymo, it's heading this autonomous miles driven per year. And we are seeing that there are some companies, they still didn't start doing this. And they are now going inside this market, and they need to somehow to achieve this mileage in a short time to compete against other competitors. So how we do face the challenge inside the organization? So we have something we call it ADAS model-based testing toolchain. It is a toolchain which can be programmed actually in any language which is able to create tests and test scenarios as many as the requirement is needed. What does this mean? It's a dynamic library which is able to cover all the corner cases and requirements per test case, which means if I want to park or to test a parking scenario, it will create me as many parking slots as possible to cover parallel parking, perpendicular parking, and diagonal parking, with different spaces, different objects. If there's a pedestrian, no pedestrian, moving objects, traffic, and so on. So this is the ADAS model-based testing toolchain. What we have is, it was developed actually on Java. It is a multi-threaded library. On the other hand, we have the algorithm that we need to test. Let's say object classification detection, or the simplest case is only blind spot detection or auto park. And at the end, we have something called the simulation tools. Inside the organization, we use many simulation tools such as ROS, robotic operating system, which we build our sensor model inside. We use CarMaker from IPG, from Kazuo. We use Virus. We use many other platforms, and we have some platforms which are built inside the organization. And the solution is to integrate the simulation tool with this model-based testing toolchain in order to simulate the environment around the vehicle, to simulate also the vehicle and simulate the parameters and the corner cases which are talking about. So this is how we face the challenge inside software verification. This will allow us actually to cover corner cases which cannot be done on a road because of some safety issues, and we can reach also the mileage which we need to provide to the OEM as fast as we can, because we are always we're having the deadlines of start of production or some software releases, some hardware releases, and so on. So I'll talk a bit about the deployment, how we do it. So assuming we have the model-based testing toolchain, it will just start creating the test cases. And on the other side, we have the simulation platform. For an instance, it's a CarMaker. And with this interface, which can be a UDP connection, a COM, or a shared memory, we request to set the vehicle speed of our ego vehicle to an X kilometer per hour. And simply the simulation will get this information and will set this vehicle speed to this velocity. After that, let's assume we want to get the steering wheel angle, for an instance, for a parking scenario. So the interface will just deliver this message to the simulation platform, and the simulation platform will send us again the steering wheel angle inside the model-based testing, and so on. At the end of the model-based testing, let's say, process, we will have many test cases which are based on real feel of the environment. What does this mean? Instead of letting the tester to set the speed to X and saying, yes, after 5 seconds, please stop. Please put the steering angle to the full maximum on the right and start reversing. We are actually getting this information from the simulation platform, because the simulation platform simulates the car with the parameters, which brand we have, the dimensions of the car, the dimensions of the environment itself around the ego vehicle, and so on. So actually the test case which is generated which simulates the real behavior and the real environment, which is as the same as outside on the street. So I will talk about also a bit more about the deployment. So this is a car maker screenshot which can detect actually some objects around the ego vehicle. What we do is we try to create as many deterministic behavior scenarios as possible. This means from the requirement or from a customer ticket, we get all these, and then we put them in a very, very big database, which is available for all the organization on testing levels for system tests, software validation, and component tests. And then we start to test our algorithms using this database for every release, which will save us some time before actually testing the vehicle on the road. So we can check, let's say, a smoke test, we can check some requirements, safety requirements, and so on before even releasing it inside a car to be tested. And of course, if AI is involving in this, then we need to test some primary requirements for AI to ensure that it is safe to be tested on the road. So how we deploy it? We have the simulation tool, as I said. We have our Cell and Hill. For both Cell and Hill, we have the algorithm inside. But why we use Cell and Hill? So we can, in Cell, we can use the algorithm without some hardware limitations. And then we use the Hill, of course, to test the component itself with some hardware limitation. This will allow us to find bugs which are hardware dependent, which cannot be detected on the Cell. So if the algorithm works very fine, it's great. We just check it on Hill. If we have some bugs for the same software release, then we should have some doubts regarding the hardware. And this is what we do on Cell and Hill. We also do some mill tests, but basically the most important two are the Cell and the Hill. And this report will go actually to the system test to be analyzed. So in addition, from the simulation tool, we get the ground truth. If we have some requirements regarding object classification and detection, we use this ground truth to compare between the output of the Cell and Hill and the ground truth. And the model-based testing is doing this by creating the scenarios and comparing in order for us to get some reports. So after we get some reports, we will have all valid and invalid test cases or requirements. For the valid test cases, we are using them to make some new training sets, which can be done, which can train some AI algorithms inside our organization. So this new training sets can be then uploaded inside the database, which I mentioned before, and it can be used to train some new algorithms, which we are sure that these requirements are okay for such systems or functions. So deployment inside car maker. As we know, the car maker has some ego vehicle inside, some simulation parameters. We can add pedestrians, traffic lights, bridges, and so on. So what we do, we have a scenario, and inside the scenario, we have our car model, which is the ego vehicle, which needs to be tested. What we do is we always developed two sensor models. The sensor model means, for an instance, an ultrasonic model, a camera model, a radar model, or a LiDAR model. What we use two models. One of them is AI trained model, and the other is scientific model. Scientific model is basically a model which depends on radar specifications or LiDAR specifications, and it has as many equations as you can imagine. It's very complicated, and the AI sensor model is trained using real data, which we have collected through several years, to act like the sensor, or it behaves like the sensor which we have on the ground. And those two will fetch or will append the data or the information of the sensor inside our hill and cell. In addition to the ground truth, then we get our report. So this is a bit of a depth inside what we do inside car maker model. This is done also on ROS and on virus. And for the AI sensor model, I think I have, yes. So this is a screenshot of a developed AI sensor model for the laser scanner. And I think, for an instance, maybe it's hard to differentiate which one is real and which one is simulated. And this is what I want to say, that like they are both not simulated, they are both not real. One of them is real and one of them is simulated. And what we did is we trained our sensor model to behave actually like the LiDAR which we have on the ground. Regarding the trained sensor model, we used the data we have collected in order to first train and secondly to validate. So actually we also use our training sets or our recorded traces in order to validate our AI, and this is what we do, and so we call the sensor model qualification. So before even starting with the validation of AI algorithms or any algorithm, we need first to validate our sensor models, and this is what we call a sensor model qualification. So the sensor model qualification, the objective of it is to evaluate our sensor models. If it's AI or even mathematical model, we need to ensure that they are really working right. And this is what we call a validation of the components which we have on the pipeline. And it can be used for test-driven development methods. And it can be used as a reference for the developers actually to enhance their sensor models. Because for every release of a hardware or of a new product, this simulation, this sensor model qualification will help those developers to say, okay, we have a sensor model which reaches 70% of what we expect. So they go furthermore to validate it. And of course, when it reaches the full maturity, it can be used as an acceptance criteria for the sensor model inside the organization or for the OEMs and so on. And this is what we are trying to do now with the Valeo team in Cairo, leading it Ahmed Chib now. And for the deployment, so for a very simple scenario, what we do is we get a deterministic test case, which is from the real world, and we create the same simulated trace inside car maker, and we are trying to figure out if we have some differences. This is in easy and simple words. What we do is we have the real data, the simulated data, we compare them, we apply some KPIs, and then we can do some, we create some reports which can be sent, of course, to our system test to say, yeah, please use this sensor model for, let's say, for object classification or for parking or for detection. This is a screenshot of the report that we get. So we get many KPIs, and what we see is only a scan point visualizer, and those are both from simulation. We just did it for presentation. So what we see in blue is a scenario which we have a car in front, and what is in red is a truck. So what we do is actually and literally we compare two scenarios, two deterministic scenarios with the same distance, the same conditions, guardrails, ground reflections, and so on, and we compare them to each other. In addition, we have many KPIs which we are using, like field of view matching, clutter scan points, and some intensity differences, incidence angle differences, the first shot on the ground, how many objects can we detect per frame, and we do also what we call bug-to-bug testing, which we get the same trace which is simulated and the real trace, and we apply them on sill or hill, and we compare the results, and actually it should be the same, so we can simulate the literal behavior of our hardware sensor. And then we get this report which says, yeah, we have some blockage state inside the sensor, which says, yeah, we have some blockage of dirt or of raindrops or some ice. And then we say, okay, we have some blockage detected on this and we need to solve it. So this is a demo of one of the parking scenarios which was done using a simulation model. Let me just check if it works like this. No. So again. So what we did here is, this is a platform which already been developed by Valeo, and this is Canoe. So I'm using the interface of Canoe to send a REST bus simulation or the vehicle bus inside the ECU. And what we do is I am ordering the ECU please to park. And when I start, actually this simulation platform will send the data of the ultrasonic to the ECU. In this example, I put a curb in the middle, and this curb should not allow the car to park because we don't have the enough distance to park. So it will abort this mission, and the ultrasonic data will be sent to the ECU, and the ECU say, oh yeah, I will not park because it's not enough. And I redo this now without a curb, and we will see that the car will park in a very perfect S-curve maneuver, and in what we call one-time parking scenario. So it will detect first the first edge, it will detect the space, it will detect the second edge, and using the algorithm inside the ECU, it will park a very perfect in a very perfect S-curve maneuver. This was done with ultrasonic. I will show you now also some laser scanner deployments which we have done last year, and I presented it before. So this was regarding ultrasonic. Let's go back. And then, so this is for object classification and tracking for car maker. I will first show you the movie, and then I'll show you what we did with sill and hill. So this is a very simple scenario which have many objects which are interacting with our ego vehicle, including bicycles, some wheelchair pedestrian crossing the street, some buses, and so on. And I will show you now what we have done using our sensor model. So this is the same scenario. I know it will be a bit hard to imagine it, but this is actually the same scenario where we do some object classification and object detection. So the car will stop saying, yes, there is a cycle which is going on. This is our ego vehicle in the middle. So now it will just stop on the traffic light. And this is actually what we can do using sill and hill. So we can check if our algorithms, including AI algorithms, are working fine or not before we release it inside a vehicle on the street, which is moving. So this is one of the deployments which we have. This is what we saw, and now it will come to the point of having some also vegetation inside our scenarios. We can see here that we have lane marking which can be detected or tested we can see some vegetations on the right, on the left, which sensor model is reading from car maker and sending it directly to the algorithm of our LiDARs and laser scanners. And this was done last year, where we can actually measure all the scan points, all the point clouds, all the intensities, and send it directly to our cell and hill. And in addition to that, we have what we call weather conditions, because sensor simulation platforms are not really able to simulate weather conditions. And for that, I will show you some of what we did. So first, I will show you the spray simulation. What we did is we tried to simulate the same behavior as we see inside our real traces, and this was done for our sensor model, where we can really simulate a trace where there is a wet road on a highway with spray on our LiDARs. And the second one is rain, where we actually simulate the rain which is coming directly towards our laser scanner. So these and many, we have some blockage simulation, we have dirt simulation, blockage, we have temperature simulation, and we are trying to combine all this in one concrete sensor model. And after that, of course, we'll do the sensor model qualification in order to emulate the real behavior. So this was done from my side, but I want to mention one thing, that we are always depending on sensor on the V cycle, where we have some traceability, but with the existence of AI, we can't only actually remodel, but inside every testing level, we should have some iteration, which we develop this algorithm, we test it, we deploy it, and then we develop again in order to ensure that we are reaching some what we call the zero mission. And if we only use the V cycle in order to do this, actually we will not really reach this point, and in what we call level 5 autonomous driving. Thank you for your attendance, and I'm open for questions. I'll just check if I have some questions here. I don't know, Arton, if you want to take the lead also.
Well, I can jump in here. Thank you, first of all, for your presentation. We did get a question in just now. I will read it out, and maybe you can talk about that for a minute. That is it possible to evaluate the performance of algorithms based on so many KPIs? Some of them may be contradictory. For example, initialization time versus false alarms. And the question is, how do you handle the high number of KPIs?
Well, what we do in our validation department is we get the KPIs directly from the OEM. So the OEM requires us to get some KPIs, and we send them the results after we finish. So actually, we do not really evaluate the KPIs unless you are talking about the KPIs of the sensor model qualification. For that, we have our own data scientists, which are able to detect the false positives and false negatives, and actually build new test scenarios for the model qualification in order to avoid these contradictions.
Okay. If there are any more questions, please send them in now. Otherwise, I think you can. Oh, see, there's the next question right there. Before I was just wanting to pass on to my colleague. This is great. There are some questions coming in right now. Then we can continue with our Q&A. So the next question would be, where and when do you walk into limitations of the simulations?
Okay, we have many, let's say, limitations. First of all, of course, you cannot really simulate the behavior of a real sensor. We use simulation in order to just save some of the effort that is done on the road. The limitation comes from the fact that the hardware with its algorithm and the embedded hardware, which is real-time, is different. The simulation framework, which is a real-time framework, and it's not a real-time hardware. This is one limitation. The other limitation is the effect of an instance, the sound effects or the noise or the light effects. This needs a lot of work, and this is where we come to a limitation. We have like some problems, such as in the LiDAR. If you want to simulate some noise coming from the sun, this needs to be done in a very deep, with a very deep knowledge. So we have some limitations. In addition, we have some scenarios, actually some corner cases that cannot even be done on simulation. Such corner cases where, because the simulation platforms are physical engines, so colliding two vehicles, sometimes it doesn't work because of some physical engine requirements and specific physical engines limitations. So these are basically the limitations that I am facing. I'm sure there are many else what the developers are facing even now. I'm pretty sure. But yeah, these are the main that we are facing right now.
Thank you. Then the next question is, how much is the depth accuracy calculated using stereo camera?
For this, I need to ask the developers, but I will answer you in a bit. When I ask them, I will just write it.